Hello students, welcome to the course on operating systems. In today's class, we'll study file system implementation. In this lecture, we'll discuss the directory implementation and file allocation methods, the free space management, efficiency and performance, as well as recovery. The main objective behind today's discussion would be the study of block allocation and free block algorithms and the trade-offs related to the performance.
Well, we know that disk is a direct access device and hence it generally gives us a flexibility to store or rather access files in a faster and an efficient manner. But the main issue generally comes up then when multiple files are to be stored on the disk. So the space which is available on the disk need to be properly utilized so that it doesn't have so many of the gaps or left blocks, and the files whichever are stored on the disk, whenever the user wants to access them, they are quickly accessible. There are three generic techniques which are available for allocating files on the disk. One technique would be called as contiguous allocation, second would be called as linked allocation, and the third would be called as indexed allocation method. Okay, let us now discuss the contiguous allocation method. Okay, so we understand that for a user a file is a single logical unit of information. Okay, and if I assume that this display presentation is a single file, then I would prefer reading it from top left to the bottom right, starting with the word contiguous allocation followed by each file occupied and so forth, going till the last few words like offline, downtime or online. Okay, so this way I'll be moving around the file, and if I read it randomly, so obviously you might not be able to link it in the proper spirit. Whatever meaning it wants to pretend, it might change. If I say performance is simple, location, space, file, external, each, contiguous, length. Oh, I don't know, like if this would lead to something sensible if I speak it so randomly. Okay. But if I try reading it like each file occupies a set of contiguous blocks, best performance in most cases, simple only starting location, and so on so forth, saying knowing the max file, external fragmentation, need for compaction, offline, downtime, or online. So when I read the file like this, you get to have a better feel and interpretation or understanding of this file. Okay, the same may be the case when the file is actually stored on the disk, or maybe a little different. When we use the contiguous allocation method, it is ensured that all the information of the file is stored together in the same place, back to back or contiguous space on the disk. The disk is generally split into smaller partitions, which we generally call them as blocks, and all the blocks are of the same size. Likewise, every file that was to be stored on the disk, that is also logically split down. I would also use the word physically again because actually the file is broken. The file is split down or say partitioned into the same equal sized blocks, and the size of each file block would also be equal to that of the disk block. Assume that I have a disk which can store 100 lines of information against the total space of 20 blocks into it. So if this can store all the way 100 lines and it has 20 spaces or 20 blocks to store it, so obviously one block with equal size would be having a capacity of storing 100 divided by 20 equals to 5 lines per block, right? And if I have some file called file A which is containing 50 lines of text into it, then if this file has to be stored on the disk, I would require 15 divided by 5 is equal to 3 blocks. Similarly, for another file B which has to store 50 lines inside it, that file would require 50 divided by 5 is equal to 10 blocks to be stored on this disk. Importantly, this method has to ensure that the 3 blocks required by file A to be stored on the disk, and similarly those 10 blocks which the file B requires to be stored on the disk, they all must be contiguous on the disk. Hence, we would say that this method is quite simple. Correct? This method is quite simple, as we just need to understand how many blocks are required in order to store a file, and along with that, when you know that this file particularly requires 5 blocks, or it requires 10 blocks, or it requires 3 blocks, you just need to find those 3 or 10 blocks together somewhere on the disk. And you just need to record what is the starting location of this file, because if you say the file starts from location number 1, so it contains 5 blocks, so automatically it will have first, second, third, fourth and fifth space. If a file starts from 10th location and it has to occupy 3 blocks, it will go to block number 10, block number 11 and block number 12. So this way, let's now study this with help of another example. Let us suppose we have a disk which is split into 32 blocks of equal size, starting with block number 0 going till block number 31. Then, supposing that this has to store certain files on it, the names like count, the tr, then the mail, then the list and the f. Each of these files would require certain length for its storage. Assuming that count needs 2 blocks, tr needs 3 blocks, mail needs 6 blocks, list needs 4 blocks and f needs 2 blocks. Then, across the space of 32 blocks, these 2 plus 3 plus 6 plus 4 plus 2, that is 5 and 10, 15 and 2, 17 blocks of space needs to be occupied somewhere. Okay, so out of these 32, 17 blocks have to be occupied and split across these 5 different files, or rather allocated across these 5 different files. We could see in this particular diagram the shaded segments. The shaded segments indicate the place by which we can identify which space is given to which file. As we could see, the file count needs 2 blocks and starts from block number 0, which is indicated from here. If I start from block number 0 and I need 2 blocks, that means I'll go till block number 1. Similarly, there is a file called tr which requires 3 blocks and has been allocated the block number 14 as its starting block. So I would find somewhere the occupancy of the file tr starting from block number 14 with 15 and 16 blocks occupied. So total it occupies 3 blocks, block number 14, block number 15 and block number 16. Similarly, talking about another file called list. List requires 4 blocks and its allocation starts from block number 28. So if I read it here, I will require the 4 blocks something like this: block number 28, block number 29, block number 30 and block number 31. These 4 blocks have been allocated to the file called list. So in this way we could observe that all these files, whether it is count or is it f or is it tr or is it mail which has been occupied here or is it list, all these files have been allocated the consecutive blocks for their storage. So thus, coming back, we could find that this method is quite simple in its operation and offers best performance in most of the cases, because accessing a file is quite simple. Then, when you talk about such kind of situations, you have to address certain issues around it. Okay, as we see that certain number of blocks which are required to store a file, they all need to be contiguous. This will invite certain challenges to us or certain requirements. Okay, if the required number of blocks are not available on the disk, then we could not store this file on this disk. Secondly, If the required number of blocks are available on the disk but they are non-contiguous, then the file could not be stored again. Hence, the implementation of contiguous allocation method has to address certain concerns like number one, you need to find the space for the file on the disk. Then, you also need to know in advance what is the maximum possible size of the file which the file can store. Okay, so when you have the answers to these two questions, so it makes the method a little better to go with it. But sometimes, rather I would say most of the times, you might not be in a position to predict what would be the actual size of a file in advance, because talking example of the very presentation itself or any kind of assignment that you make, sometimes you assume that you have to write an answer of 5 lines, but when you find an easy question, a question rather which is easy to answer, you can end up writing more than 5 lines as well. A question which you seem is difficult to answer, writing 5 lines also is a very big task for you. Okay, so this way prediction of what will be the actual size or maximum capacity of a particular file would not be very much accurate, would not be very much true to a user. Hence, these two challenges become important, and these two questions actually become important to answer for a user while they have to implement the contiguous allocation method with the operating system. Additionally, this method also suffers from the problem of fragmentation. Fragmentation is a situation wherein some of the free space is observed on the storage media that could not be allocated to a file which requires to be stored on the disk. Fragmentation can be internal or it can be external. When we talk about external fragmentation implies that the number of blocks which are free or available on the disk, but they could not be allocated to a file just because of the fact they are not contiguously placed on the disk. That means free space is randomly distributed across the disk. In order to overcome this problem of external fragmentation, operating system may have to perform an overhead activity which is called compaction. Compaction is a process by which the already allocated files are moved to a new space within the disk so that all the free space or the free blocks are brought together into a single larger pool of free blocks, so that any new file which has to be stored on the disk can get adequate amount of available space out of these contiguous free blocks. Similarly, the fragmentation can be internal. Internal fragmentation implies that there is some extra space allocated to any given file X, which is more than the exact actual size of the file X. For example, in the thing which I discussed earlier, that a disk has 20 blocks, each block can contain 5 lines. Okay, so if a file requires 5 lines to be stored, it will require only one block. If a file contains 20 lines to be stored, it will require 2 blocks. If a file contains 15 lines to be stored, it will require 3 blocks. But what if the file has only 6 lines? Now when the file has 6 lines, it will occupy one complete block and one partial block, and that partial block will actually use one line of space and will not use the remaining 4 lines of space. Hence, the total allocation to file X would be 2 blocks, whereas its requirement would be less than those 2 blocks. But it cannot completely store into one lesser block than this, because with one block it can store 5 lines, not 6 lines. Hence, those 4 extra lines which have been allocated to that file X, that is something which we call as internal fragmentation. Well, another extension to this contiguous allocation method could be extent-based systems. There are certain new file systems like Veritas which uses a modified contiguous allocation scheme that is known as extent-based file system. The extent-based file system generally allocate disk in blocks of chunks, or maybe these chunks are generally given a term called extents. An extent is actually defined as a contiguous block of disks. The extents are allocated for file allocation, and the file may be comprising or allocated to more than one extents. Let us study the next method of allocation called as linked allocation. In this case, you can store a file at random or scattered blocks on the disk. It is again divided into multiple blocks. Likewise, we have in the contiguous allocation. Okay, the disk would be split into multiple blocks, same with the file would also be split into multiple blocks. But when it comes to allocation, the blocks may be randomly placed on the disk. Okay, so this kind of approach gives an advantage that it doesn't suffer from the external fragmentation, in which when the space is already available on the disk, it could not be allocated to a file just because of the reason that it is non-contiguous. So the linked allocation, each block would contain a pointer to the next block where this file has to be stored. Then it will have to call for a free space management system also whenever a new block is needed. I would try to coordinate this with the data structure topic of linked list that you have already studied. A linked list generally contains two pieces of information. Every node that is organized over there, that has two parts of information inside it. One is the data, or the actual value that or the information that the node is storing, along with the pointer to the next node that will contain the next part of the information. Okay, same way, this free space management system would try to manage all these nodes or all these blocks as something like nodes. Okay, so this avail management system or the free space management system will locate a free block from the disk anywhere randomly and accordingly update the linked pointers of the already allocated blocks, and the file would try to manage the same way. So reliability can be a little of the problem in this particular case, because generally if the pointers get corrupted, then it will be very difficult to restore the entire file back. And secondly, because it's a pointer based concept, so it will require more manipulation, and it might take a little more time to access the file from the disk, because the disk head would have to move from one block to the other in order to get the particular file. Okay, and if you want to avoid this kind of delays, you can increase or improve the efficiency of this mechanism by grouping or clustering multiple blocks, and if you do that, then you actually tend to increase the internal fragmentation problem. Okay, so that means if we try to counter with one problem, then you can obviously have to face a trade-off with the other issue. As discussed, in the linked allocation, each file would be seen as a linked list of disk blocks, and the blocks may be scattered randomly or anywhere on the disk. So each block would be having one pointer section, and the remaining part would be the data or information inside this particular file. Okay, so this way a file would have multiple such blocks together. The mapping would be like, if the block size is 512, it will use 511 lines for the information, and the remaining data would be used, right, that one location would be used as a pointer or the address to the next block, which is the sequential block in the file, logically sequential block in the file. Let us now try to read it with the help of an example. Assume that on this disk we have a directory or scattered across 0 to 32 blocks of the disk space, There is a file called keep which requires somewhere around 5 blocks for storage. Okay, so if this zip file requires 5 blocks of storage, 5 blocks required, then these 5 blocks could be placed at anywhere in this disk of 32 blocks. In order to implement the file system, you have to take note of which is the starting address, means which is the first block allocated to this file, and subsequently, which is the last block allocated to this file. Now, it doesn't mean that in this case, if the starting block number is 9 and the last block number is 25, then all these blocks would be summed within 9 to 25. Answer is no. Okay, so as we could see into this particular example, the index table will lead the file G to be accessed starting from block number 9. Okay, then after that, block number 9 increases or directs the pointer or redirects to block number 16. Okay, so that means first you go to number 9, then you move to number 16. First you see 9 followed by number 16. So this is how you tread the path. After block number 16, reading this information, you will have to reach to next block. The next block as redirected in this example is block number 1. So you go talk to block number 1, read the contents. Block number 1 redirects you to the next block, which is not block number 2, rather it is block number 11. This is again random allocation. Wherever you find a free block, you go and allocate that. Okay, don't worry even if the next block is not the very contiguous block to the currently allocated block. After 11, you go to the block number 25 directly. Okay, so this way you could see that 5 blocks have been allocated: block number 9, block number 16, block number 1, block number 10, and block number 25. And same way, block number 25 does not redirect to any place. No further redirection, that means this tends to be the last block. And this is double verified by another example or another system table value that is called as the ending address of this particular file. So your file is Jeep, its starting address is block number 9 and its last block allocated is block number 25. Between 9 and 25 it can move across any block number, whether it is before 9 or it is after 25 or it is anywhere on the disk. Okay. The next method, indexed allocation method. This is again a customized implementation of the linked allocation method in which rather than every node point to the next node, this file would try to maintain its own index block. An index block is a block which will try to contain an information of all the block numbers which are allocated to this file. Okay, and so logically you will find that every file would have an index table like this. This will be an index table. So this index table would have multiple entries which will relate to each and every single block that is allocated to this. So these are the blocks allocated to a file. Okay, if I mark it as red or maybe I highlight it in red, these are the actual file blocks, and this table highlighted with yellow would have the entries or pointers marked to these blocks actually available on the disk. Let us study indexed allocation with the help of an example. I have a file called G and it has an index block placed at disk block number 19. So on this disk of 32 blocks, okay, starting from 0 to 31, block number 19 will be treated as the index block to this file called G. Now, this index block is responsible for telling us or giving us the information about which all blocks have been allocated to this file. I hope you remember the block numbers which have been allocated to this file. The block numbers which were allocated to the file Jeep in the previous example of linked allocation, they were block number 9, followed by block number 16, followed by block number 1, followed by block number 10, followed by block number 25, which was its last block. Okay, so the same information in the same order would be placed into this index. So if I talk about this index node which has been expanded here, I see that this index node number 19 has multiple entries or multiple pointers inside it. The first pointer will link to location number 9, second pointer will link to location number 16, third pointer will link to location number 1, next will link to block index 10, and the last one would link to 25, and the remaining are marked into an invalid or a null location indicated by -1. So if we just indicate that particular section and try to emulate with the thing called 9, 16, 1, 10, and 9, 16, 1, 10, and 25. So this is how the pointers have been set. Block number 19. First it goes to index block, normal block number 9. Then this index block 19 issues a next pointer to block number 16. Then it issues a pointer to block number 1. Then it issues a pointer to block number 10. Then it issues a pointer to block number 25. And rest there are no more pieces of information. So obviously when this file is read and displayed back to the user, it will be in the sequence first the content of block number 9 followed by block 16 followed by block 1 followed by block 10 and 25 in the last. So the indexed allocation method would have certain properties related to it. That number one, it would require every file to maintain an index table, and if this index table has to be stored, one extra node has to be given to every file. Okay, but because the information is stored in form of an index, then these files or these nodes of the file could be accessed randomly. So this mechanism is free from external fragmentation, but this provides us with a disk space consumption overhead in terms of an extra block which is called an index block. If we talk about the linked allocation, we used only 5 blocks. But if we talk about the indexed allocation to store the same file G, which otherwise would have used only 5 blocks for data, it is actually using 6 blocks, which includes 5 blocks of data and 1 index block. Same way, if you have 10 such files, then the 10 blocks out of 32 would be used to actually store indexes. Otherwise, in the linked allocation, those 10 blocks would have been used for storing a few more files. The mapping from the logical to physical file in the disk would be in the terms of maximum file size. Obviously, that would be in the range of 512 bytes, as in this case of example that we have been following for this entire. So when you have to store even larger files, which size is unbounded, or we would say that they have more than 512 or the standard size of each block, then this can be done with the help of multi-level indexing or a linked scheme or a combined mechanism of the linked and multiple level index schemes. So in this index allocation with linked scheme, we can use the technique when multiple index tables or multiple index nodes are to be generated. So what will happen is you will create a linked list of the index blocks. That means if file 1 has 3 indexes, the first index will point to the second index and the second index will point to the third index block, and first index will also point directly to each and every individual data node. Similarly, the second index node will also point to each and every data node, and the third index will also point to the each and every data node or data block which has been allocated to that file. In case of index allocation method with multi-level index for storing larger files, you actually try to maintain, rather than a chain of index blocks, you try to create a one high level index block. Then this high level index block will point to multiple sub index blocks, and each sub index block will eventually point to the data blocks which are actually allocated to the file. That means one parent index block followed by multiple children index blocks or sub-index blocks which will in turn point to the multiple file data blocks. So in this two-level index example, if we talk about, then we could, address that if every pointer requires 4 bytes, and if we try to, take up a 4K blocks, then these 4K blocks could store around 1024 such pointers if the size of every pointer is 4 bytes. Okay, in the outer level index. So this will imply that if each of the 1024 index tables are created or index nodes are created, then each index node would also eventually have 104856 7 data blocks pointers, and this will eventually lead to a file size as large as 4 GBs. Let us see the model visually. We have the basic file system entry, say file heap. File heap will point to the outer index table. Then this outer index table will have multiple pointers, and these pointers will separately point to each and every individual sub-index table. So this is the example of two-level index, multi-level, index allocation scheme. Okay, so this is index table 1 or sub-index table 1. This is sub-index table 2, sub-index table n. Okay, and likewise, this index table will point to one data block, second data block, third data block, and so on. It will have its own data blocks. Similarly, some data block pointed by the entry at second index table, sub-index table entry, some data blocks pointed by second entry, third entry, and so on. Similarly, this would also point to certain number of entries around. Okay. If we talk about the Unix file system UFS, which is also known as the BSD fast file system, that uses a combined scheme which takes a mix of the linked allocation as well as the indexed allocation at multiple levels. The file system generally treats every disk split into 4K bytes per block, and it will have 32-bit addresses obviously related to that 4K bytes. Okay, and the entire information about the file, as we know that in the Linux or a Unix-based file system, is stored in form of inodes. The inode structure will have 15 pointers. Out of these 15 pointers, the first 12 will directly represent the link, or they will directly redirect to the data nodes or the data blocks. Okay, and any file which requires a space of 12 into 4K, somewhere around 48K storage space, that file would not require any further linking beyond these 12 links. And the remaining entries number 13, 14, and 15, those three pointers would not be the direct representation to the data blocks, but rather they would be an indirect pointer to those data blocks. When it comes to indirect pointer, that means they will go to some multi-level indirection with the help of indexing. The first pointer will point to a single indirect block, which is an index block that will not contain data, but it will contain the addresses of the next segment of data blocks. Then, if the number of data blocks go beyond that, in that case, the 14th block would come into picture. This 14th entry would be a double indirect block, which will have further two sub-levels of the index blocks. That means from the 14th block you will point to one index block, and this index block will further point to another level of index blocks. Okay, so this actually multiplies to a large scale. And similarly, the 15th entry would be a triple indirect block. That means it will have further three more levels of index blocks in order to reach out to the desired data blocks. Let's see over here. Apart from the basic information about any file, okay, so we are taking the information regarding what is the number of blocks available into the file, Then there are 12 links to the direct blocks. This is the first section. So these 12 links would be used, and these will directly point to data, data and data. Okay. Then the single indirect block will point to an index table. Index table will be pointers to multiple data blocks. Okay. The double indirect one would point to one index table. This index table will further point to multiple sub-index tables. Okay, and these sub-index tables would further lead to multiple data blocks. And same way when it comes to triple index, it will point to multiple, you know, one triple index table. Then these will point to one more level of index tables, and these index tables would further point to one more layer of index tables that will eventually move to data, data, and data. Okay, so this is how the data nodes would be mapped. Now, after all this discussion, we come to a point where we need to choose or decide which one is the best. So basically, the best method would not be a simple interpretation because there are so many aspects by which one method would be better and the other one would be a little weak on that. Okay, so generally, the best method would depend upon the file access type that we need to have. So if we want to choose one method, it might offer certain advantages, whereas choosing the other one would offer a different set of advantages. Okay, a contiguous method is generally great or good when it comes to sequential as well as random access files. Okay, because whenever the data has to be accessed, if the file's entire set of contents are all together, it will take less overhead in terms of file access. Linked method is good for sequential but might not be that very good for random because it will require a lot of head movement when you have to randomly access the parts of the file. Then you generally need to declare the access type at the creation of the files. You can either decide whether you have to go for contiguous allocation or linked allocation, but these sort of flexibilities might not be very much leveraged by different file systems. Index file system is generally complex because it requires a lot of links management, and more the links or pointers being used, then it is the additional overhead in computation of and reaching out to the desired data block. Then the single blocks access could also require two index block reads and then one data block read. That means in order to reach out to the data block, you will have to actually perform the read operations, two read operations before reading the actual data, and these two read operations will be reading the index block addresses. So in order to avoid something, you can tend to add certain instructions to the execution path so that you could avoid one step of input-output activity, which could be generally reasonable. Okay. For example, in the iPhone 7 Extreme Edition 990X, edition 2011, generally operating at a speed of 3.46 GHz, that is offering a completion speed of 159,000 millions of instructions per second. Okay, so similarly, this could offer you a typical drive speed at 250 input output per second, and that could lead to reading 613 million instructions during one disk input output operation. If we talk about the fast solid state storage devices, then they could provide you the input output operations per second to the scale of 60,000, and this 159,000 million of instructions per second raised to 60,000 division factor would lead to only 2.65 million instructions to be read during one disk input output operation. Well, let's now think about the free space management on the disk. Basically, we are seeing that how the data is actually, or how the files are actually stored on the disk, and now whatever space is left behind, or means the blocks which are not yet allocated to any of the files, they have to be managed somewhere by the operating system so that whenever a new file is generated or some existing file requires more space, then In that case, the operating system should be able to cater to that request of the file and allocate it new space from the free blocks which are already available on the disk. So generally, a file system maintains a free space list in order to track the available blocks or clusters, and we obviously use the term block, and when multiple blocks are used, then they would be termed as clusters. The four different methods have been proposed here for managing the free space. Number one, the bitmap or the bit vector method. Number two, the free list method. Number three, the grouping method. And number four, counting method. So these four methods would be used for free space management. Let us see the first method, the bitmap or bit vector method. In this case, whatever are the number of blocks, you will require that much size of space or that much size of bits in order to store the status of whether a particular block is available or not. If suppose that your system has 32 blocks or your disk has 32 blocks, then you will require 32 bits on your disk additionally that would rather store the status of availability or occupancy of those each of those 32 blocks. So if block number I is currently not allocated to any of the files, then this bit will represent 1, and if that block I is already allocated to any of the files, then the availability or occupancy status would be represented by corresponding bit I as 0. So hence, block number calculation would generally be on the basis of number of bits per word into number of zero value words plus the offset of the first one bit. CPUs generally have the instructions to return the offset within the word limits. The bitmap will generally require some extra space as I discussed. For 32 block disk, 32 bits would be required. Let us take an example of a 1 terabyte disk. 1 terabyte generally amounts to 2 raised to power 40 bytes. And if the size of each block on this disk is of 4 KB, that is 2 raised to power 12 bytes, then the total number of blocks available on the disk are 2 raised to power 28. So if there are 2 raised to power 28 blocks available on the disk, it will require these 2 raised to power 28 bits in order to represent the status of each of those 228 blocks. So this 2 raised to power 28 generally amounts to just a space of 32 MB. Imagine 1 terabyte disk using an overhead space of just 32 MBs in order to just keep the track of free blocks. Not a big deal. I think 32 MBs against 1 terabyte is hardly a measure of the percentage value. Okay, so hence this method is easy and simple to implement and especially good when you have the contiguous file allocation system. Obviously, in any kind of allocation method, this method would suffice a good one. And in case further, these blocks are also clustered. That means if you have a cluster of 4 blocks each, then obviously these 32 MB space would be further subdivided by 4 and will remain around only 8 MB of memory consumption in order to keep track of availability of that many number of clusters on the disk. Another method is the free list method. In this case, you tend to, create a linked list kind of a structure wherein this linked list will start from the first free block on the disk and each free block will point to the next free block followed by a sequence next and so on. I hope you could recall the actual allocation of the previous files. As you could see, one file was allocated to block number 0 and 1, another was allocated to block number 6 and 7, then a third file was allocated from block number 14 till block number 16, the fourth file was allocated from block number 19 till 24, and one file was allocated from block number 28 through 31. So if we try to if we try to see the free space management list for this, a linked list would start from the very first free block. The first free block is block number 20. It will start from, block number 2. It will start from block number 2. Okay, the free list head would be present and would be pointing to block number 2. Block number 2 will in turn point to block number 3, which will in turn point to the next three blocks, that is 4 and 5. Then 6, 7 are already occupied by some 5. Then 5 will jump onto block number 8, sequence to 9, 10, 11, 12, 13, and eventually 14, 15, 16 are already occupied, so after 13 it will be pointed to 17, 17 will lead to 18, 19 through 24 are already occupied, so 18 will lead to 25, then 26, 27, and because after that 28 to 31 are already occupied, so 27 will set to null. Okay, so this kind of method is good when even it will use relatively lesser amount of space? No. Probably, in order to manage all these pointers, you need to store 4-byte addresses or 2-byte or 1 byte or whatever is the total number of blocks available. So accordingly, that amount of space has to be consumed in order to manage all these pointers. So linked list method cannot get contiguous space easily. So in that case, linked list method can be used. It generally, does not need to traverse the entire list of free blocks, because the moment you find certain number of free blocks, those can be allocated to a new file very easily. Another method would be grouping and counting. So in case of grouping method, this is similar to the indexed allocation. You try to modify linked list to store the addresses of next n minus 1 free blocks. Okay, that means the first free block will contain the pointer to next remaining free blocks, just like an index. And each of these nodes will eventually point to all those next free blocks pointers. In the counting method, because the space is frequently continuously used as well as freed with contiguous allocation or extent or clustering, the counting mechanism can also be used. The counting mechanism tends to keep the addresses of the first free block, and along with that also counts the remaining free blocks following the first free block. Okay, the free space list will generally have the entries that contain the addresses as well as counts. So addresses and counts, both the fields of information are managed in the free space implementation. Recovery. So obviously when a lot of data has been stored on the disk or some files have been stored on the disk, a user wants a system that is not just efficient or quick to retrieve the files, but it should also be reliable. So sometimes when you lose certain files, you need to recall them back or recover them back by different kinds of mechanisms. Okay, third party tools are so many available in the market, but yet whatever is the basic thing that the operating system or any user can do is around consistency checking as one, backup and restore as another method. In case of consistency checking, the operating system will try to compare the data in the directory structure along with against the actual data present on the disk blocks. For example, if the table says that block number 1, 3 and 7 are occupied, and when the actual data bits on these three blocks are analyzed, then they do not indicate some valid values against those things. So this would tend to, slow down the access procedure while accessing, while retrieving the files from the disks. So the consistency checking will compare the data in the directory structure with the data blocks on the disk and will try to fix or rectify the inconsistencies observed, if any, in this course of comparison. This procedure is generally slow and will sometimes also lead to a failure in accessing the data files. Then, certain system programs may also be used to back up the actual data on from one particular storage device or media to the other storage device media. Okay, So that means you just tend to create multiple copies of one particular file. And if you back them up, then obviously if you want to re-access them against a loss or a failure, you have to restore them by recopying them from the backup. Okay, so a lost file can be restored from the backup disk by recovering. Okay, thank you. So with this, we come to the end of the chapter number 14 on file system implementation. If I try to recall, we talked about contiguous allocation methods, we talked about extent-based systems, we talked about linked allocation, we talked about different types of indexed allocation methods. After that, we discussed the compared, like which method would be better based on certain parameters. Then we talked about the mechanisms for handling free space on the disk, and finally we discussed the brief on recovery mechanisms. Thank you and have a good day.